Welcome, this is Professor Ridge and today's lesson 2.4, Complex Numbers. Our first learning objective, add and subtract complex numbers. First we need to talk about what is a complex number, and before we can talk about complex number we got to talk about this I. Right? So expressing square roots of negative numbers as multiples of I. Alright, so if I asked you, now remember this square root symbol is really the principal square root. So if we're saying what squared is equal to 9. And there's two answers. There's -3 squared is 9 and 3 squared is 9. But the symbol is defined to be the non-negative square root, so it's only 3. So the answer is just going to be, square root of 9 is 3. And then this, if I wanted the negative square root, then I would put the negative out in front, and that would be -3. Now, what if you had a negative inside? So what if I did the square, what's the square root of -9? Well, the problem is, what squared is -9? So what squared is -9? Well, up here, we know that no matter what we square, if we square -3, we get +9, just like above. And if we square +3, we still get +9. So what squared is -9? The answer is there's no real number. Okay, so if it's not a real number, then we say, okay, well then it's a fake number. It's an imaginary number. And so that's how we say, all right, let's define the square root of -1 to be this, what we call the imaginary unit. Okay. And we also define that I squared is equal to -1. So that fits in saying the square root of -1 is, if we say what squared is -1, well that's I squared. So I is the square root of -1. Okay, so we're going to kind of start there with our complex numbers. So we're going to define the imaginary unit as this. So then if I want to find out what's the square root of -9, we're going to add one more rule to this too. We're going to say, note, I'll just write it here, note that if P is a positive number, then the square root of -P, so we got a negative number in here, is going to be defined to be the square root of -1 times the square root of P. So we have to do this first before we do anything else. So the square root of -9 is going to be the square root of -1 times the square root of 9. And then from the example before, we know that the square root of -9 is 3. The square root of 9 is 3. And then this, by definition, that is just going to be I. And typically we write the number first and then the I after it. Okay, so the square root of -9 is just 3I. Alright, now we're ready to talk about imaginary and complex numbers. So a complex number is a number of the form a plus bi, where a is the real part of the complex number and b is the imaginary part of the complex number. So if b equals 0, then a plus bi is a real number. So if b is 0, you're just going to get the real number part. So it'll be a real number. If a is 0 and b is not equal to 0, the complex number is called a pure imaginary number. Okay, so it's just purely imaginary. An imaginary number is an even root of a negative number. That's where you get the i's in there. So basically, if we have 3 plus 4i, we call this a complex number. If we have, so let's see, if b is 0, so if I had something like 5 plus 0i, so this is a complex number, but it just equals a regular real number, whole number, in fact, in this case. Let's see, what else? If a is 0 and b is not equal to 0, so if we had 0 plus, say, 2i, we call this just this is purely an imaginary number. Okay, so imaginary number. So we got a complex number. They're all complex numbers. So if we go back from earlier lesson when we talked about the real number sets, complex numbers include all the real numbers, but it also includes the imaginary numbers as well. Okay, so this is the biggest number set. Plotting a complex number on a complex plane. So we can't plot a complex number on the real number axis, right, which is the x-axis typically. So, but we can plot it. We can make the y, the vertical axis, we'll call that the imaginary, and then the x-axis is the real number line. And so the way you do this is to determine the real part and the imaginary part of the complex number and move along the horizontal axis to show the real part of the number, and move parallel to the vertical axis to show the imaginary part and plot the point. So if I wanted to do the 2 plus 3i, I'm going to move to 2 on the real axis, and then I'm going to move up 3 on the imaginary axis and plot the point, and that point will represent 2 plus 3i. Okay, so the y-axis is your I, and this is your real axis, the x-axis. Let's try one more example. 2, plot the complex number 3 minus 4i. So again, the x-axis is going to be your real part, and then the y-axis is going to be your imaginary. So a is 3 and b is negative 4. So we're going to go 3 on the x-axis and negative 4 on the y-axis, which is now we're thinking it is the imaginary axis. So we got the real axis, imaginary axis. So this is your 3 minus 4i on the complex plane. Alright, now we're ready for the adding and subtracting complex numbers. So just as real numbers, we can perform arithmetic operations on complex numbers. To add or subtract complex numbers, we combine the real parts and then combine the imaginary parts. So you can see in the rules here, we got 2 complex numbers. We're adding them together. You're going to add the real parts, so the a plus the c. That'll get you the real part of the sum. And then you're going to do the bi plus di, and it's kind of like combining like terms. You're just going to add the number parts, b plus d, and then just leave the I alone. So a lot of times I'll tell my student, look, forget it for a moment. All right, let's do an example. So what is example 3 for A? They want you to do 3 minus 4i, so that's your first one, plus 2 plus 5i. So that's your second complex number. So what we're going to do is we're going to, well, back to what I was saying. A lot of times I'll tell my students, just forget for a moment that I is anything special. Just pretend it was a variable like x. How would you simplify this? And it's just, you're going to combine like terms. So since it's addition, we can drop these parentheses and rearrange it. So 3 plus 2 would be 5. So you wouldn't write this down, you just write 5. And then you're going to combine the i's. So negative 4 plus 5 I, which is just 1 I, and you don't have to write the 1. So it's just 5 plus I. All right, and then 3b, now subtracting the same thing. Now be careful when you subtract. You're going to subtract a minus c and then b minus, because you got to distribute the minus sign. So it's b minus d. All right, so let's look at 3b. Example 3b, negative 5 plus 7i minus negative 11 plus 2i. So typically what I do is I just, again, just for a moment, just kind of ignore that they're complex numbers. Just think of them as algebraic expressions. So let's see, I can drop the first parenthesis since there's nothing out in front of it. This one I have to distribute the minus sign, so negative minus a minus 11 becomes plus 11, and then minus 2i, right, because negative 1 times 2 is negative 2, so you can think of it either way. Alright, now I'm going to combine like terms, the negative 5 plus 11, and again I wouldn't write this step, just to kind of emphasize what we're doing. So that's the negative 5 minus a minus 11. So that would be 6. Oops. I don't know what I did there. 6. And then 7i minus 2i. So 7 minus 2i is 5i. And then that will be our answer for that one. So again, it's nothing more than just combining like terms, right? You could think of them as algebraic expressions for a moment and just do what you normally would do. That's kind of the way I approach it. All right, moving on to our next objective. Let me see if I can bring that page up. Multiply and divide complex numbers. Multiplying complex numbers. So multiplying complex numbers is much like multiplying binomials. The major difference is we work with real and imaginary parts separately. Okay, so let's start with multiplying a complex number by a real number. So we have 3. And again, 3 is technically a complex number, right? But it, like when we defined it before, the imaginary part is 0, so it's just basically a real number, but it's still a complex number. You got to remember that. All right, so how do we multiply complex numbers? So if one of the numbers is just a real number, you're just going to distribute, just like, again, just for a moment, think of it as just a algebraic expression. Like if I gave you 3 times 6 plus 2x, you would have no problem say, oh yeah, you just distribute 3 times 6 is 18, 3 times 2 is 6, and then you just leave the x there. Well, that's exactly how you multiply this. So 3 times 6 is 18, 3 times 2i is just 6i. And then you can see this is in the complex form, a plus bi. And that's simple as that. All right, let's look at example 4. Multiply 4 times 2 plus 5i. So it's still just a complex number being multiplied by a real number. And it's the same idea. We're just going to distribute. So 4 times 2, 4 times 5i. Again, you don't have to write that step. Just in your head, 4 times 2, we're distributing. That's 8. And then 4 times 5 is 20. And then just leave the I there. And that's it. As simple as that. Example 5, multiplying a complex number by a complex number. So we're going to multiply two complex numbers, a plus bi form. Again, the way that I typically have my students do this is if I gave you this 4 plus 3i, and just pretend it was an x for a moment, and 2 minus 5x, and you saw this, right? A binomial times a binomial. You're going to use the FOIL method. You're going to distribute. So 4 times 2 plus 4 times negative 5x. So your first outside, inside. Now we're going to do these. 3x times 2, and then 3x times negative 5x, sorry. And then you would get 8 minus 20x plus 6x minus 15x squared, and then you would combine the like terms, so minus 14x. Now here's the problem. It's not a binomial. I mean, they're not algebraic expressions because it's not x squared. So if we, okay, I'll explain that in a second. Let's go ahead and multiply this out. You're going to use the same method. You're going to distribute or use the FOIL method. So I'm going to skip this step. So 4 times 2 is 8. Just going to do this in my head. 4 times negative 5i is negative 20i. 3i times 2 is 6i. And then 3i times negative 5i, so don't forget the negative, will be negative 15i squared. We're going to combine these like terms, 14i, but we got to remember that I squared it's not like a variable. It's I squared is defined to be the imaginary, so I is the imaginary unit, it's square root of negative 1. I squared is negative 1. So you got to remember that. And then negative 15 times negative 1 is positive 15, and then you're going to combine these like terms, and we get 23 minus 14i. Okay? So that's the difference. It's I and I squared. They're not variables. They're specific things. I is the imaginary unit, which is square root of negative 1, but we just leave it as I. And I squared, you got to convert it to negative 1. Dividing complex numbers, the complex conjugate. So to divide complex numbers, we need to talk about complex conjugate. And it is a complex number, a plus bi. The complex conjugate of a complex number, a plus bi, is a minus bi. It is found by changing the sign of the imaginary part of the complex number. The real part of the number is left unchanged. Now, when a complex number is multiplied by its complex conjugate, the result is a real number. When a complex number is added to its complex conjugate, the result is a real number. So we have this nice property here. So if we have a plus bi, and we multiply it with its complex conjugate, a minus bi. So if you think about binomials, this fits that form of, if you take a sum with its difference, this is one of the special ones that you're supposed to memorize, a squared. So if you FOIL this, you get a squared minus ab plus ab equals b squared, not equals. And then b times negative b is minus b squared. And then these two terms cancel out because you got a plus and a minus, and you get a squared minus b squared. So this fits that same pattern. You get it's a difference of squares. You get the a squared minus, but it's not b, it's bi. And then that's going to give you a squared minus, and you got to square both of these, b squared, I squared. And then what we just talked about a minute ago, I squared is negative 1, and then negative 1 times the negative here will get us a squared. Well, I'm going to go ahead and show it. So we get a squared plus b squared. So that's going to be a shortcut. We cut out all the work in the middle, and we memorize that a plus bi times a minus bi is going to be a squared plus b squared. Okay, so that's an important concept. We want to memorize that one. And then here, when you add two complex numbers, the result's a real number. Oh, notice there's no I left in here. A squared plus B squared. So this is going to be a real number. And then on the second part, if you added A plus BI plus A minus BI, so you drop the parentheses, you get A plus A is 2A, and then the plus BI minus BI cancel. So you get just a nice whole number there again. Or real number, I should say. Okay, so that's those 2 points there. This one here, it's the big one that you know how to do that, right? You can skip all this work. You square the A, square the B, and it's going to be plus. Where if they're just binomials or algebraic expressions, there's no I in it, right? That's a difference of squares. But when you do it with complex conjugates, you're going to add, not subtract, because it's the minus. The minus becomes plus. Example 6, find the complex conjugate of each number. So basically, if this is the number, this is our complex number. And then we want to find the conjugate. So for A, you're just going to switch the imaginary part. So it's going to be 2 minus I square root of 5. And that's it. And then here, the real part 0, and again, you're just going to switch the sign of the imaginary part. So it'll be plus, which you don't have to write the plus. So it's just 1/2 I. Okay? Don't overthink it. Example 7, dividing complex numbers. So divide 2 plus 5i by 4 minus I. So we're going to write the division problem as a fraction. So we're going to take 2 plus 5i divided by, so fraction bar, 4 minus I. So remember, the fraction bar means divided by. So now determine the complex conjugate of the denominator. So what's the conjugate of the denominator? So you switch the sign of the imaginary part, so plus, and then multiply the numerator and denominator by the fraction of the fraction by the complex conjugate of the denominator. Basically, we're multiplying by 1. So the fraction, we're going to multiply both the numerator and denominator by the conjugate of the denominator. Okay, exactly what it says here. All right, now we're going to simplify. So we're going to distribute the top. So here's the fun part. The top you're going to distribute. So 2 times 4 is 8. 2 times I is 2i. And then distribute the 5i. 5i times 4 is 20i. 5i times I is 5i squared. And then on the bottom, we're going to use the shortcut. We're going to square it. 4 times 4 is 16. And then minus I squared becomes plus. And then you do the number 1 squared, which is 1. So you just get 17. Okay, so remember, I squared is -1. So minus the minus becomes plus 1. So the bottom's just simply 17. The top, now this again is another -1. -1 times 5 is -5. So we got 8 minus 5. Okay, I'll write it. Let's combine these two. 2 plus 20i. And then we got plus 5 times -1, which is -5, plus the 8 is 3, plus 22i, all over 17. Now, we want to write it in a plus bi form, so we're going to split this up into two fractions. So 3/17 plus 22/17. And then you put the I like in the middle where the division bar or fraction bar is. Okay, so it's 22/17 times I. On to our last learning objective, simplifying powers of I. Simplifying powers of I. The powers of I are cyclic, right? There's a pattern that repeats. Let's look at what happens when we raise I to increasing powers. Okay, I like to start with 0. Book starts at 1, but that's fine. By definition, for exponent rules, anything to the 0 power is 1. So that's also true for the imaginary unit. I of the first is just defined again with exponent rules. Anything to the first power is itself. I squared, by definition of imaginary numbers, is -1. Now here's where we have to become tricky. So I cubed, you can think of it as I squared times I to the first using exponent rules. A to the n is equal, A to the n times A to the m is A to the n plus m. So we're using this back in reverse, right? So 2 plus 1 is 3. So I can split it up. And then now we know that I squared is -1. And I to the first is just I. So we get -I. And then this is basically, this pattern is going to keep repeating. So if I go I to the fourth, that's I squared times, actually I like to do it this way, which is -1 squared. -1 times -1 is 1. I to the fifth, that's I squared squared. So if we do this rule, A to the n to the m, you multiply. So 2 times 2 is 4, but I want 5, so I need the one that's left over to make 5. So I get -1 squared times I, which is 1 times I, which is I. So you see how it's repeating? So if I go I to the 6, I squared cubed is 2 times 3 is 6, so I don't have any left over. So that's -1 to the third power, which is -1. Okay, and then I to the 7th, this will be our last one. So if I go 7 divided by 2, that's 3. Remainder 1, that's the way I think of it. Or if I want to work backwards, 2 times 3 is 6, plus 1 gets me 7. So that's -1 cubed times I, which is -1 times I, which is -I. Okay? So basically you're going to, if you have, well, let's look at the next example. Example 8. They want you to simplify the power of I, and it's I to the 35th power. So what I do is I say, all right, let's divide 2 out. So if I think of 35 divided by 2, that's 17.5. The 0.5 is the remainder 1, because if you work backwards, 2 times 17 is 34, and you need one more to get 35. So now this is -1 to the 17th, which is, if you know, -1 raised to an even power would be +1, -1 to an odd power, 17's odd, -1 to an odd power is -1. So we get -1 times the I. So it's -I. Okay, that's the way I do it. And that brings us to the end of the lesson. So make sure to practice the exercises at the end of the exercise set, and I'll see you next time.